Okay, so now let's do a mechanical FE type question for limits and fits. So the end goal here is to give you an overall concept or idea that will help you answer FE type questions, specifically when you're looking at limits and fits in this case. So we know in the FE handbook they talk about this stuff on page 439 in the new FE handbook 10.0.1. If you do not have that, you can just download it on the NCS website for free as a PDF. So it's handy because they actually provide a nice figure on their limits and fits on page 439, and we can see that in the paragraph it says the designer is free to adopt any geometry of fit in shafts and holes that will ensure the intended function. So we know over time sufficient experience with common situations has resulted in the development of a standard, and the metric version is the newer and most commonly used. So the metric version specifically, I believe what they're talking about is the section under that on 442, and that's when you essentially look at the feature control frame and look at the LMC, MMC, the maximum material condition, and the feature control frame and the datums and so on. So that's what they're talking about there. But the most important thing, it says in there on that last sentence, the standard specifies the uppercase letters are always referring to the whole. So uppercase letters are for the whole and lowercase letters are always for the shaft. So we have to know that. But for this example, we know we're focused on this figure here, and we're told given the following shaft and hole cross section, complete the following table assuming metric tolerancing. And we know here the table is down here, and this is what we're going to complete. I know this is not a multiple choice question, so maybe they'll ask you a drag and drop question, but obviously this is too much for one FE type question. They might ask you the limits, they might ask you the tolerance, and so on. But I'm trying to tackle a lot of things in just one question, which is not that bad if you go slowly, I think, which is what we will do here. So some definitions though, I want to quickly say that on that same page on 439, they have definitions. The limits are the maximum minimum size of the part, whether you're looking at the hole or the shaft, right? The hole has limits and the shaft has limits. In this case, we have a shaft hole assembly, but that's where the limits. Then you have the tolerances. Delta D is for what? Capital D is for which one? The hole, right? Capital D is for the hole. So delta D, they denote it as delta D, the tolerance for the hole, and delta D, lowercase d, is the tolerance for the shaft, right? For the shaft, the lowercase delta D. And so that's the tolerance, the total amount of specific dimensions permitted to vary. So it's the difference between the maximum and minimum limits of the dimension. And we will find that for this question. And I want to state delta D and lowercase delta d, I actually put a figure. It's very similar to what we have on that page on 439. But we know the tolerance for the shaft is lowercase delta d. And you see how it's the maximum limit, d max minus d min. So that makes sense. And it's the tolerance zone in green. And for the hole, we take the maximum limit d max here of the hole minus low limit d. So the low limit is just d for the hole, and that's going to be delta d for capital D for the hole, the tolerance for the hole in orange. So just note this is there, and in the handbook they present a similar figure, right? So the basic size is the size which the limits are calculated. So we know these are usually the diameters, and they are usually selected from a table of preferred sizes. And we know I think on page 441, they give us the international tolerance grades, and they also give us some basic sizes if you had to choose based on your lower limit and upper limit, and based on the IT values and so on. But we will not discuss that when we solve this. We're just going to do this table, but just note that's there when you have basic sizes. And when you're looking at the upper and lower deviation, you can select the basic size, you can find the lower and upper deviation, then you can find whether you have the best type of fit you want, lowercase c, lowercase d, lowercase f, g, h, and so on. That's also on another table in 441, right? So that's gonna be the basic size, and we know it's the same for both components. And typically what always we do is take the basic size of the maximum hole diameter, which we will see in our example. Then we have the deviations, the difference between the basic size and the hole or shaft size. Upper deviation is going to be the difference between the basic size and the permitted maximum size of the part. Lower deviation is the difference between the basic size and the minimum permitted size of the part. And the fundamental deviation is the upper or lower deviation that's closest to the basic size, right? So we will find these, then the fundamental deviation is either going to be the upper or lower, whatever's closest to the basic size. And so that is the figure, and you can, so I'll attach this in the description below if you need to refer to it. So let's focus on this question. Let's begin by the limits for the shaft and the hole, right? So what's the limits for the shaft? So let me label the shaft. The shaft is this thing, and the hole is gonna be this, right? The hole, I'll use blue, this is the hole. So we have the shaft and the hole. Let's find the upper and lower limits, which are the limits. So for the shaft, the upper limit is just the 0.51, the lower is 0.47. And that is the diameter symbol. So we have an upper limit of 0.51, a lower limit of 0.47. So you can write it like this, 0.4, so 0.47 to 0.51. So this is the upper, right, limit, and this is the lower limit. So upper, lower, and upper limit. For the hole, same exact thing. So the upper limit for the hole is 0.50, the lower limit is 0.49. So we lower is 0.49, upper is 0.50. So this is up, this is the lower limit. Okay, so we have that. Then the basic size. What's going to be the basic size for the shaft and the hole? So we know on the FE handbook, in the FE handbook on page 449, they defined it. The basic size, or the nominal size, capital D or lowercase d, is it limits which limits or deviations are applied when we apply those lower and upper deviations is the same for both components. So in this case, we will have one size, and you always take the maximum hole size. So in this case, it's going to be 0.50, and that's all you do. So it's going to be 0.50 for both of them. So the basic size is 0.50 or 1/2 if you are looking at that. So it's 0.50. So then the tolerance is going to be which one? The tolerance in the handbook, you have a tolerance for the shaft and a tolerance for the hole, right? And delta D, capital D is for the hole, delta lowercase d is for the shaft. And let's use this figure. All we do is what? You just take, let's say for the shaft, you just take the maximum limit minus the lower limit. For the hole, you just take the maximum limit of the hole minus the low limit, and it gives you the tolerance. And that's in the handbook as well in the figure, right? So you just take the difference between these. So you do 0.51 minus 0.47. That's the tolerance for the shaft. So it's 0.04. And for the hole, you just take that difference and you get 0.01. So we have the tolerance. Now the next one is the MMC and LMC. So if we define what we mean by MMC and LMC, we have different conditions for shafts and holes in this case. So for shafts, it says MMC, maximum material condition, is defined in the handbook, and it's where the part has the most amount of material or weighs the most. So if you think about that logically, when it has the most amount of material is when it has the largest shaft diameter, and then it would essentially have the most amount of material and it would weigh the most. So for shafts, it's always going to be at the upper limit size because that's what has the most amount of, the largest diameter. Then we have the least material condition. LMC is defined as what? The part has the least amount of material and weighs the least. So we know when the part, a shaft specifically, has the least amount of material is a smaller hole diameter, and it's going to be the lower limit size and the least amount of material where it's going to weigh the least. Now for holes, it's different. So the maximum material condition for a hole is the smallest hole diameter, right? So as you decrease that hole diameter, if you can imagine that, you have the lower limit size, and therefore you decrease the hole diameter. Now you have more material, right? You have more material if you picture a cross-sectional area, and then it would weigh the most. So note, for maximum material condition for the hole, it's always the smallest hole where the lower limit size. The least material condition, it's going to be the largest hole, so the bigger cut we make through that hole, and it's going to be the upper limit size. We remove the most amount of material, so we remove a lot of material, and thus we weigh the least, right? It weighs the least, and therefore it's the least material condition at the largest hole size, which is the upper limit size. So that's the difference between shafts and holes. Let's go above and answer that part. So the MMC for the shaft, again, it's going to be the upper limit, right? It's going to be the maximum diameter, which is going to be the 0.51. That's going to be the MMC for the shaft. So it's going to be 0.51. What's the LMC for the shaft? It's just the other number. So the one on the lower limit, so it's 0.47. We reduce that diameter, so the least material condition for that one, the shaft, is 0.47. Then we have the hole. For the hole, it's kind of tricky. Be careful, right? The maximum material condition is when you what? When you decrease the hole size. When you decrease the hole size, which is going to be the lower limit. So it's 0.49. So here it's 0.49. Then the least material condition is going to be the 0.50, the upper limit, the maximum hole size, the bigger hole size, 0.50. So that's that, and we have that. We're almost done. Now we want to find the max clearance and minimum clearance. So now the max clearance is going to depend on the least material condition. So the max clearance, we simply take the least material condition for the hole, which is going to be 0.50 minus 0.47. So it's essentially the upper limit of the hole minus the lower limit of the shaft. So in this case, we take the max limit or upper limit of the hole, D max, minus the limit, the low limit for the shaft. So here I think there's a mistake, but it should be this. So that is actually incorrect. It should be this dimension, right? So that's going to be the max clearance, and I'll fix that in the PDF. But the max clearance, again, it depends on the LMC, and you take the LMC for the hole minus the LMC for the shaft. So it's 0.50 minus 0.47, and that gives you a max clearance of 0.03. So we have the max clearance. The minimum clearance is just the opposite. It depends on the MMC. You take the whole 0.49 MMC minus the shaft 0.51 MMC. So you take that difference, and that's going to be your minimum clearance, and it's going to be this dimension here, that dimension, and we just do that, and it depends on those MMC condition. So you do 0.49 minus 0.51, and taking that difference, we would get a negative 0.02. So now for the very last one, the type of fit, the easiest way to find that is using the following conditions. So we know you have three basic types, and they discuss three basic types in the FE handbook: clearance, transition, and interference on page 440. And we know you use it for different types of conditions, different type of assemblies, and that's all discussed under the different types. You have free running for clearance, for example. Transition, you have locational transition fit, and so on. So that's all in the handbook in the table on 440. But the basics here, you have some preferred fits. The clearance is, we know the shaft is always smaller than the hole. That's going to be that, and that's what we're talking about there. But the most important thing is the minimum clearance value, is always bigger than 0. So we always need that minimum clearance. You can just find that. If it's bigger than 0, you have a clearance fit. Then you move on the interference. So the interference, we know the shaft is always larger than the hole, and the max clearance, when we calculate that, is less than or equal to 0. So we have generally here the max clearance is less than 0. So that's an interference fit. And then the transition fit, it has to satisfy two conditions. The max clearance has to be bigger than 0, and the minimum clearance has to be less than 0. So the transition, it's in a transitional stage, right? So you could either have a clearance fit or an interference fit, and that's what's denoted in the figure here. You either have a clearance or interference fit, and it has to satisfy these conditions. That's the transition. So in our case, we just compared the max and minimum clearance values. So the max clearance and minimum clearance are these. So which one would we pick? So the max clearance is bigger than 0, and the minimum clearance is less than 0, right? So the max clearance is bigger than 0, minimum clearance is less than 0. So I believe it satisfies the very last one, right? Max clearance bigger, minimum is less than. So yeah, it should be a transition fit in this case. So the answer for the type of fit is a transition fit. I'll just say transition. So we just simply completed the whole table, and I want to finish off by saying that deviation stuff in the handbook, so they talk about the upper deviation, lower deviation. Let me just mark that on the diagram here. So I'll use blue for the upper deviation. So the upper deviation, you always start at the upper side of the shaft, so the very max limit or upper limit of the shaft. Then you go to the lower limit of the hole. So essentially it's going to be this dimension. So this is the lower limit of the hole, right? So you go here. So you start at the upper limit, the maximum limit of the shaft, go to the lower limit of the hole. So that's going to be your upper deviation. Then you have the lower deviation. You start at the lower limit, low limit of the shaft. Then you still go to the low limit of the hole. So that one, we know we're still going to the low limit of the hole. So we start at the low limit of the shaft and go to the low limit of the hole. So this is your lower deviation. So in this case, we have the upper and lower deviation. So the upper deviation would be, again, you just take the low limit of the hole minus the upper limit of the shaft. So you do the low limit of the hole, we said is going to be 0.49 minus the upper limit of the shaft, which is 0.51. And if you do that math, you get negative 0.02. So that's the upper deviation. The lower deviation, you do the upper limit, the low limit of the hole, which is still 0.49, minus the low limit of the shaft, which we said the low limit of the shaft is 0.47. And that equals a positive 0.02. So essentially the fundamental deviation is just 0.02. And that's important when you're trying to determine other stuff, especially when you look at deviations for shafts and when you essentially want to use these equations. Let me go down here. So these are all in the handbook, and let's say you want to find the diameter max. Use your fundamental deviation here, and that's applicable here as well. But that's how you find those, the upper and lower deviation. And that's it. Thank you.